Again, it's a very interesting case study, very similar to what we talked about, very similar to what we covered. The ideas are not any different, but there were some new learnings that we had in this case study also, and some parts of it we discussed. And let me summarize it in a quick 5 minutes conversation once again. So this was my data set. Again, we have the different features of the customer, the limit balance, education, marriage, age, payment status, bill amount, past 6 months bill amount, past 6 months payment amount, how much payment you made against your credit card. It's a credit card data set, right? So you typically get a bill, then you make the payment for the bill. So this is giving all the typical transactional metrics against that customer's credit card account. Okay, so we're looking at the historical data, how the customer has used and interacted with the credit card account. Okay, how much bill he or she has incurred, how much payment he or she has made, what is the credit limit, what is the payment status, were there any late payments, did the customer pay on time. So these are all the different features of the customer that we have. And we also have default payment next month. So we also have a flag variable that we are using to track the default payment next month. That means we are saying that, hey, like this particular customer with today's reference point, we are trying to understand, will this customer default the next month? Next month is the month of June that will come. So we are trying to understand, will this customer default the next month? So that is what we are constantly trying to predict. So we already have a rich amount of labeled historical data. We have a lot of labeled data right now with us. So we have ones and zeros as per the labeled data that we have right now. And we are trying to figure out whether the customer will default the next month or not. That is what we are trying to do. So 1 means the customer will default and 0 means the customer will not default. So that's the inference we are able to get. So if you see the status, 1 means the customer defaulted the next month, and the status of 0 means the customer did not default or will not default the next month. So that is how the statuses look like right now. So 1 is you will default and 0 is you will not default. That's the inference. Okay. So we are trying to build a classification model based on this data. Okay, and I also told you that you should make it a point to drop these columns. ID column is obviously not important because this is not a good predictor of default status. Okay, a person's employee ID or any kind of identity features, these are basically serial numbers. Basically, these are roll numbers. So roll numbers have nothing to do with your actual default status, right? Row numbers have nothing to do with it. You should always make it a point to eliminate and drop these kinds of columns, and also these other columns like sex, education, marriage, because these kinds of features will contribute to bias. So whenever you encounter these kinds of features which have a potential to contribute to bias, you should always make it a point to drop these kinds of features. Otherwise, your models will end up being biased. Okay, so we did that. We did that here. Rest of the solutioning was very straightforward. And if you see, I dropped these columns and I went ahead and built a baseline model. This is some fundamental EDA I try to do. You can see limit balance, for example. I'm looking at the distribution plot for limit balance, and you can see that this was part of an earlier conversation we had yesterday. We talked about histograms and skewness and all those beautiful things in the class. And if you recall, this is a right skewed or a positively skewed distribution. Okay, why do we call it a right skewed or positively skewed distribution? Because most of the limits are average to low. Most of the credit limits are average to low. And that is the general pattern, right? I mean, if you today take a credit card, most of the normal customers will typically get a credit limit of, let's say, close to 50,000 to 1 lakh. Normally, as a starter point, you might get a credit limit which is around that range. And there are very few customers who will start out with a very high credit limit. Okay, so it's inherently a right skewed distribution that we will find. Okay, so it's important to know this because I told you that supervised learning, when you're eventually building models using supervised learning algorithms, uh, the algorithms tend to function better, especially some of the algorithms tend to work very well when you're having more symmetric and more normal data. If you have skew in the data, the models will also have a tendency to become a little biased. Because if you see this case, we have lots of examples of customers who have average to low credit limit balance basically. And we have very few examples of customers who have high limit balance. So if you're thinking from a supervised learning perspective, you have a lot of data for average to low limit balance customers, but you have very limited amount of data for let's say high credit limit customers, high limit balance customers. So maybe we don't have enough patterns to for the high limit balance customers. So these are some of the limitations that we will have, and it's always a good practice to apply something called power transformer, which is what we will do in this notebook. Okay, so how do we reduce the skew? How do we take a right skewed and left skewed distribution, and how do we convert it into a symmetric normal form? So we go and use something called power transformer. So power transformers are what we use behind the scenes. Okay, which is exactly what we will do here also. And you can actually see this is a small demonstration what I try to do. So you can see this is the limit balance, the original distribution of limit balance feature, right, which is a right skewed or positively skewed distribution with high outliers. And when I go and apply power transformer, you can see this is the power transformation that I did, power transformer. These are internally mathematical transforms and all that we perform. So moment I do that, now you can see in the new revised data frame, the limit balance is more symmetric. Can you see? So the limit balance right now is more symmetric and more normal after we perform the power transformation. Okay, coming to the modeling part. The modeling part is straightforward. Most of you did it already, so I'm not going to take too much time here. So baseline logistic model, we're getting a fair amount of underfitting. And the interesting part I wanted to clarify is this one. This is the real takeaway from this exercise. As I told you, all these case studies, each of the case studies have some takeaways. Okay. Otherwise, the template is all the same. Do the train test split, fit a model, get the accuracies, get the CV scores, build the confusion matrix. That's it. Work done. But what are the takeaways? What is the new learning from this exercise? The new learning from this exercise is this confusion matrix. If you look at it, although you're getting 70% accuracy, like, see, I mean, if I don't show you the confusion matrix for a minute, you will look at this accuracy numbers and say, hey, I think we have a decent model. I think we have a decent model, right? So we have 77% training, 77% testing. So we seem to have a very decent model. I'm not saying it's a very good model, but it will be like an average model, underfit model. There is always a scope to make it better. I told you that underfitting and overfitting are always relative terms. So there's always a scope to make it better. So here also we can clearly see that it's a kind of an underfit model. We are having 70% accuracy in training. We are having 70% accuracy in testing. So it's a kind of an underfit model. But there's a scope to make it better. There's definitely a scope to make it better. That's the idea. Now the interesting part is when you go and look at this in a bit more detail. So we are getting the predicted values here, LR.predict predicted values. We are building the confusion matrix. And once you take a look at the confusion matrix, now you start to realize that this is actually a dummy model. So this is actually a useless model. It's a dummy model. Although we are getting 77% accuracy, that 77% actually means nothing. And you know how and why we got that 77%? I'll tell you. I'll tell you how. So if I annotate, if I start the annotation for a minute, let me zoom in for a minute here. I'll zoom into the confusion matrix particularly. If I annotate, this is 0, this is 1, this is 0, this is 1, right? These are the predicted along the columns. These are the actuals along the rows. And if you look at it, the model is actually making no default predictions. So what you are seeing on the screen right now is a dummy model. It's a dummy classifier. This classification model is not making any zero predictions. Sorry, any default predictions. The classification model is not making any default predictions. This is a completely dummy model that we have on the screen right now. It is not making any default predictions. It is a completely dummy classifier. It's a completely dummy model that we have. So next time you get any test set, next time you're getting any test data and you're doing a prediction, all the predicted values are zeros. So mathematically, if there are total 6,000 records, because if you add up the numbers, you're getting total 6,000. Out of total 6,000 rows which are part of my test data, and if you do the maths, you actually have 6,000 records which are part of your test data. Out of total 6,000 sample test questions, all of them are predicted to be zero. The model is not making a single one class prediction. It's not even predicting a single record to be a defaulter. It's predicting all the customers to be not defaulters. See how useless the model is. I mean, this is in the context of a bank, a credit card. Now the primary objective of implementing this classification model in the credit card company was to identify defaulters. And look at this case. This is a case where it is not even identifying a single defaulter. It's by default saying everybody is not defaulter. Okay, all is hunky dory unless you see a big bubble building and finally the maybe the company goes bankrupt because everybody starts to default now. That's the problem, right? So important uh, concept, important learning is that accuracy will not be a good indicator of the model performance. You need to do the confusion matrix to understand exactly what's going on. And you want to know how that 77% was calculated. This is your TP, right? This is your TP, this is your TN. That's your true negative, that's your true positive. If you remember the mathematics of the accuracy, accuracy is nothing but Tn plus Tp by total. I know the number is a little hidden, but this is actually 77.7%. So if you just do the maths right now, Tn plus Tp by total, if you open up your calculator and do the maths, you will see the exact same number will come up, right? So if you do the maths right now, this is 4663. You can please open up your calculator and do the maths. You see 4663 by 6000. If you do this computation, you will get a figure which is exactly equal to 77.77%. That is how the accuracies are coming. So accuracy is not going to give you the full picture as to how the model is really doing. It is only the confusion matrix that will tell you, okay, this is how the model is doing against this class, and this is how the model is doing against this class. That's the concept, right? And this can be further uh, validated through the classification report, which is an extension basically. And in the classification report, you can also further see the support values. Support values are 4663, 1337. These are the actual number of records. So there are actually 46630 zeros. There are actually 13371 ones in the data set. And further, if you look at the classification report is going to give you what we call a class level accuracy. So not like an overall accuracy of 77%, but you can now understand what is the performance of each and every class without getting into the theory of precision recall and all that, which I shared in my conversation yesterday. But you can just focus on this metric called F1 score. At a very high level, you can look at F1 score. F1 score is like our new accuracy. F1 score is like our new accuracy, and you can think of the this as the okay. This is how the zero class is on an average performing, and this is how the one class is on an average performing. So think of it that this as like our new accuracy metric. Okay, so you can clearly see that although the overall accuracy was 77%, but the moment we look at the class level performance, the one class is performing very poorly. Zero class is performing fairly well, but the one class is performing very poorly. And probably one of the reasons could be what some of the folks raised in the session. One of the reasons could be that because we have lesser number of records for the one class. We've got only 1337 records for the one class. So the data is highly imbalanced, due to which the model is finding it very difficult to understand the patterns for the one class. This is the cross validation that we did. And you can see now we are trying out different methods. We are applying power transform and then logistic regression. How will power transform help us? Where we expect that power transform will try to mitigate some of those extreme skews we have in the data. This is again part of the data pre-processing that we are doing. And indeed, by doing that, we are able to get a slightly better model. You can see the average CV accuracies actually became better. And in fact, when after applying power transform, when I rebuild the confusion matrix, well, I mean, you'll be surprised to see that this model is much better than what I had before. So this is what I mean by the incremental improvement. So initially, the baseline model was horrible. The one class was not at all performing well, but now you can see, moment I did power transform, the one class all of a sudden has started to do better. And further, if you look at the false negatives, this is 1027, right? This is the credit card default data set. False negative is very costly. False negative means model predicted you will not default, but in reality, you are a defaulter. That is how we look at false negative. False negative means model predicted you will not default, but in reality, you are a defaulter. So you are able to, in reality, you have a defaulting customer, but you are unable to recognize those defaulters. That's a serious problem. 1027 false negative is very bad, but this is still better than what we had before. So before we had 1337 false negatives, but now the next solution with power transformer, after we reduce the skew in our data, after we made it more symmetric, more normal, we have incrementally made it better. Can you see? Next, we are applying decision trees. I will talk a little about decision trees in the next conversation. I intend to talk what is it. So far we were just using decision trees. So far I just told you, hey, there's something called a decision tree, but we don't really know what it is. I'll talk a little bit about that in a while. And this is the hyperparameter of a decision tree. This is a better algorithm. And with decision trees, we are able to get even better. Can you see? 799. So the false negatives are reducing. and we are able to get an incrementally better and better model as we go along. The F1 scores are also very, very high. So previously the F1 scores were 35% for one class, and now we can see the F1 scores are 50%. So this is the incremental improvement I was talking about, right? And this is with gradient boosting classifier, and no doubt gradient boosting will give us even better results.